Of course, we started writing this program in 2015, 2016, and it was funded in 2017. We now have the much more updated version of what's happening in New Zealand in an environmental sense in relation to our land. This new report that came out just a couple of months ago, really, about the state of the nation, as it were, in New Zealand. And I'm going to quote a few examples from this. This is the case. On the left are some bullet points. On the right are some data taken directly from this report. That 40% of New Zealand's land area is actually grazed grasslands, and a lot of it is used for grazing of cattle. The numbers of cattle have doubled enormously over the last 20, 30 years, and now to 6 million. And why is this? Of course, it's all to do with the primary produce, really, and that clearly dairy is a very important contributor to our national economy, and is expected to. Government is expecting that increase by another $44 billion over the next decade, based on what it is at the present day. It's possible because of irrigated land, and we've seen over the last 2 decades in particular an enormous increase in irrigated land. At the moment, 5% of the land area which is irrigated is 5% of the land area is irrigated, and 58% of that is used for dairy farming, and that's doubled over the last 2 decades. But 64% of that actually happens here in Canterbury. So we are very central to all of these issues in terms of both the economic but also the environmental issues as well. That's on the positive side, of course. On the negative side, there is increasing concerns about the environmental consequences of these changes. Paul Mudge, who's with us here today, has published results showing that under a lot of irrigated areas, nitrogen and carbon concentrations are lower than what they are in the non-irrigated areas. And clearly, that's of a concern to us, as we explained in the video. So we actually need to build up soil carbon stocks, not reduce soil carbon stocks. And of course, on the other side is the issue of nitrogen. We're all aware of the increasing nitrogen losses through leaching are resulting in degradation of our drinking water. On the right-hand side, you can see the dramatic increase in dairy cows. That's the blue line compared with falls in the other types of grazing animals. On the bottom down here, we have the big increase in nitrogen fertilizer. All fertilizer use has gone up, but nitrogen fertilizer has clearly gone up dramatically. So this was the problem we were facing, and there's a question of how can we provide solutions for that. Well, I'm going to go straight into the sort of mechanics of the processes that we have been working on over the last 5 years. This shows a strong coupling of carbon and nitrogen cycling, and all of those processes that we're going to talk about today. Everything from carbon dioxide uptake from the atmosphere through to carbon dioxide being riser-deposited and roots decomposing and adding carbon into the soil. And then on the other side, the nitrogen side, about inputs and losses. And the reality is that the carbon and nitrogen is well coupled, and you could argue they're in equilibrium if systems are not perturbed. But when we change the system, as has happened really at our Ashley Dean site, for example, from dryland farming on the left-hand side of this figure, low productivity, low input farming, we introduce irrigation and we bring in dairy cows and we make it highly productive. We also increase nitrogen inputs. And then on the picture on the right, which Graham just took just 2 days ago, is actually after heavy grazing. Notice the biomass has been removed, it's been taken off, and there's also the evidence of the cows have been there with leaving their urine and dung deposits behind. So when we do that to the system, we change a lot of things. We remove the biomass from grazing. We increase the inputs of irrigation, fertilizers, urine and dung. We increase leaching, as we're going to be talking about, especially on the source of Ashley Dean. There's also the concern about nitrous oxide emissions as well, which comes particularly from the urine which is applied to the paddocks. And so what we do essentially, we have actually decoupled the system. And in order to recouple it again, we need to be concerned about the management we're going to do, but we also need to find scientific solutions to say how can we recouple those systems again. And I argue that it's really in the soil microbiology and the inputs and losses to those systems where the solutions can be found, and this is where we have focused our effort. When we started out, we talked about solutions to manage the tensions, this nexus between increasing productivity and minimizing the environmental impacts and exercising creative hunger, because they were the critical the points we needed to optimize how they all come together. We wanted to deliver solutions which would not affect profitability, but would reduce nitrogen losses. And we did this calculation with the help of Dairy and Z when we put the proposal together. But presently, there's using current best management practices across Canterbury, an extra 31,885 hectares could result in a 70% decrease in nitrogen leaching. So if good management were practiced, then essentially we could reduce nitrogen leaching across the area. But the goal of the program was that if we could go 10% further than that, 10% further than best management, that would allow essentially an additional 10,000 hectares of headroom for continuing to add nitrogen system at its present rate. And that would actually be a farm gate value of $122 million per year in terms of the milk. Now, I guess as the years have progressed, we've put less focus on the economic gain. It's important, but I mean, you don't have to use that headroom for establishing more farms. You can actually use it to improve the environmental outcomes. And our whole approach has been looking at new discovery, and we're going to talk a lot about that in the first part of this morning, the science discovery that people have done. We're going to talk about how we scaled that from molecules up to farm paddocks. We're going to talk about the modelling and synthesis later this afternoon in terms of how we can extend what we've already know into what it means in a more general sense. And we've integrated that, as we're going to hear from Hirini shortly, into a Moriora systems framework in order to blend Western science and Maori thinking in terms of how can we work together to effectively solve these problems. That was the science we did. Obviously, that's coupled with end-user engagement and communication. So what did we decided we would go to Ashley Dean to work. It's what's Ashley Dean's 30-40 kilometres from here, owned by Lincoln University, a farm which is a highly productive farm converted 5 years ago, and that you saw in the video there. One of the advantages is, of course, is that it enables us to do research there in a commercial setting. But also, one of the big advantages, this is a map of the soil across Ashley Dean, and the yellow area which we were working in is effectively the same soil type across that system, and therefore we were able to avoid working across different soil types as part of the analysis we used. But one of the challenges is the stony nature of the soils. Incredibly stony, these soils. 50% stones in the top 30 centimetres gets down to 70% of stones as you go down further. And this is so typical of where so many of these land use changes have occurred to create from dry land into dairying. Using this land, it's fragile, it's very highly drained, it doesn't retain water, it doesn't retain nutrients. And so there is the concern about what leaching aspects would be and how can we solve those. So we put together some hypotheses at the start that carbon and cycling, nitrogen cycling in these stony systems was very much dependent on inputs and outputs of carbon. But we could regulate that, we could manipulate that by changing the amount of carbon that plants are putting into the system in order to manipulate the nitrogen losses and reduce the inputs of nitrogen. And we also wanted to establish the relationships between carbon inputs, how can we manipulate those through irrigation or grazing management or using fodder crops? How will they modify the nitrogen transformations which lead to reductions in nitrogen losses? And on the left of this figure is the microbial work that just illustrating that we're doing. We looked at DNA and the processes. regulating nitrogen and carbon cycling. And on the right-hand side, we're looking at the paddock scale. And in between, we've got molecular work, we've got work we're going to hear about this morning in chambers, in controlled conditions with soil samples. We're going to hear work about lysimeters, which we're going to hear about soon. We're working with chambers, and then we're working at the field scale. So we have stretched across that whole range of molecules right to the farm scale. This is the carbon balance of the field site. This is why I just want to point it out to you how complicated it is. This is why it's been quite challenging. We've got grazing animals on a grassland here. We've got the processes listed in terms of inputs and losses of carbon. But in order to assess, has there been a change in carbon, we need to look at all these components. The net change in carbon for the ecosystem is Ca, which is the inputs of carbon, from photosynthesis, of course. CD is the additions of carbon from dung and urine. CF is any fertilizer that's been added on. And then we have a whole lot of losses of carbon from respiration, both from the soil and from the plants. And then, of course, we have the leaching losses, Cl. And then we have the most important thing that we can manage, the losses through grazing, through removal. That's the Ce component. And then when you add on top of that the nitrogen balance as well, it gets more complicated. But similarly, we can look at net nitrogen changes in relation to inputs through fertilizer, inputs through dung and urine, and losses through grazing and leaching and export. And notice that in the center of this, we still come back to, it's these linkages of the processes between carbon and nitrogen cycling, which has been the focus of our work. So this is the work at Ashley Dean in particular. We worked at two sites, a non-irrigated Lucerne and an irrigated Lucerne. Why did we choose Lucerne? Well, again, it's looking back, is different from where we are today, but Lucerne was a crop which is deep-rooted, it grows well in dry conditions, it's highly productive as a forage crop, which can be grazed and can be used for cut and carry as well. So that's where we focused, because the nature of our experiments that we set up in terms of Lucerne. We're going to tell you about these large lysimeters that we established, and we're going to see those tomorrow for any of you who'd like to come to the farm tomorrow. We're going to talk about exchange measurements of greenhouse gases between the soil, the vegetation, and the atmosphere. We can't repeat this on a lot of different treatments, so we chose Lucerne to be our model, which we would use, and then we would integrate up to the paddock scale and test it against real measurements in the field conditions. So that's this is the last slide of our program, essentially just to introduce what we've done because I've not presented to you any of the detail that's going to come through all the talks as we go on. But there were 31 of us here and now around the globe, actually, who have been involved in this research, and there's been a big input. We've got a list of publications on the table of scientific publications coming out from our research. You're welcome to take that, and of course we're happy to talk to you more about that. 3 PhDs awarded from the program, and we just have one of those people here this morning, and Andrea's going to come and later on from California, where she's working to tell us about her PhD work as well. We've had the engagement, and thank you, welcome people from Europe, from ECAN and MPI, who are here, and we've also had engagement with Overseer, which is the end point of wanting to progress our work. And of course, with Hiran's help, we've engaged with the local iwi and their management plan for the system.